we'll complete the topic NP completeness. So let's start. So in our course Design and Analysis of Algorithms, so far we have studied multiple problems and how to solve them, right? And also we have analyzed their time complexity. So there are many problems that we are able to solve efficiently, where efficiently means in polynomial time, like say minimum spanning tree or fractional knapsack or matrix multiplication or normal sorting algorithm. So these problems we had polynomial time algorithms or efficient algorithms. On the other hand, there were some problems for which we studied algorithms, but these algorithms in worst case the performance is actually exponential, like subset sum, n coin or Hamiltonian cycle or traveling salesman problem, right? So these categories are problems we consider as hard problem, where these are easy to compute. Now question is, like if a problem is hard, if we know the problem is hard, then we'll not try waste our time trying to develop an efficient algorithm for it. Instead, we'll see how to manage it. But how can we prove that a problem is hard? What is the proof of it? Means how can we establish that there is no available efficient algorithm for it? So this topic is about that, a class of problems. We have different class of problems like P class or NP class or NP complete class and even NP hard class. So we'll study which problems fall in these classes and how can we prove that a problem is a hard problem or it belongs to say NP complete class. Okay. And why exponential algorithms are bad, that we have seen this if we look at these growth functions of time complexity, then we can easily understand. Here these are polynomial, where these are exponential, and we can see that as the input size is growing, number of operation, how it changes. So for log n or order of 1 or order of n, it does not grow that much number of operation with element size. But when coming to exponential time complexity, we see that small increase in the input size increases the number of operations so much, right? So that is the problem, that these problems, the exponential algorithms, maybe it can handle smaller input, but when we go to large input size, number of operation will be very high and a computer will not be able to solve it, right? Fine. Also we'll see that a problem, the two problems may look similar, but still one problem can be easy and another problem can be hard. There is an example of finding path in a graph, right? So in a graph, when you are finding the shortest path from some start vertex to your destination vertex, this finding shortest path actually an easy problem, and we have many known efficient algorithm for it, like Dijkstra's or Bellman-Ford. But if we tweak the problem a little bit and we ask to find what is the longest path, though this problem looks similar, But for longest path there is no known efficient solution, and it is actually a hard problem. Right? So we have to be aware of these differences also. And this small change in problem definition can make it very hard. And why do we care about proving a problem is hard? Because once we know the problem is hard, we will not waste time, as I said earlier, trying to solve them efficiently. Instead of that, we can opt for heuristic based solution, like where these approaches solve the problem most of the time or most of the cases in reasonable time. In worst case, it may take exponential time, but we don't worry because it is solving in most of the cases in polynomial time. So we can develop such heuristic based solution, or we can go for solving approximately. That is, we don't want optimal solution, we want a near optimal solution. So we don't want to spend exponential time, we'll spend polynomial time and find a near approximate solution, and we'll be happy with that. Or in other cases, if we know the input size can be small, we can stop worrying about the time complexity and we can use the exponential time solution also. So these are different approaches possible once we can prove that the problem is hard. Fine. So before going to that discussion how to prove the problem is hard, we need certain concept that we need to discuss. First concept is verification. So verification means, so there can be two versions of a problem where here, suppose this Sudoku problem, here we are trying to solve the problem, means we are trying to come up with what is the solution. But solving Sudoku, there is no non-polynomial time algorithm, so it's a difficult problem. But if I give you a solution, can I verify is it correct? Yes or no? So to verify it, how will verify? So we'll check every row. Does it contain all the unique numbers 1 to 9? We'll check every column. Does it contain all the unique numbers 1 to 9? And we'll check every box. Does it contain all the numbers or not? And if all conditions in all rows, all columns and all boxes, the constraint are fulfilled, we can say yes, it is a correct solution. If not, then we will say it is not a correct solution. So this is called verification. So verification means I will give you a solution, probable solution, and you will verify it. And to verify it, how much time is required to verify? So you have to go through every row maybe and every column. So it can be done, the verification can be done in order of n square or polynomial time. So we can verify in polynomial time. Right? So remember this concept of polynomial time verification. That given a solution, we can verify whether the solution is correct or not, and can we do it in polynomial time. So polynomial time verification. One more concept that we need to understand is decision problem. So far we have seen optimization problems, right? Where we are asked to find the minimum or maximum for certain problem. For example, if I say traveling salesman problem. So in optimization problem we ask what is the minimum cost tour. Minimum cost tour that will visit every vertex exactly once and come back to the starting vertex, and the cost will be minimum. This is the optimization version of the problem. Now we will consider another version of the problem called decision version, where instead of minimum cost tour, we'll ask the question, is there a tour of cost less than equals to k or cost k? Okay. Now, this is similar problem. Instead of finding the minimum, we are asking, is there a tour of cost k? Right? And here, the output will be not the tour, but it will be, output will be in yes or no. Okay. So, decision problems, answer will be in yes or no. For optimization problems, you have to find the minimum or maximum solution, right? So why we are talking about this decision problem? So we'll see later that we want to relate multiple hard problems. We want to say that two problems, let's say A and B, these are similar. Now, two problems will be difficult to relate if their outputs are different. Let's say one is TSP, another one is knapsack. Okay? Or even we'll see. So these two problems are different. It will be difficult. But if we take decision version of the problem, where this also will output yes or no, and knapsack also output yes or no, this will help us to relate two difficult problems. So we'll consider the decision problem instead of optimization problem, right? Okay. So one thing here you need to note down is that if the decision problem is difficult, then the optimization problem also will be, means if we can solve the decision problem, then we can solve the optimization problem also. So we'll discuss on this point later on. Fine. Okay. So let's come to, here. The question we are asking, can we verify a given solution quickly? Okay. And we can see that this decision version of the problem, with verification we can do for all the problems. Like Hamiltonian cycle, we can check given a cycle is valid or not. TSP, we can check whether the tour cost is less than equals to k or not. NQueen, we can check given a solution, is there any conflict or not, right? So this is not a correct solution, we can verify. So these problems where the solution can be verified efficiently in polynomial time, these problems we'll call as NP problem. Okay. So what is NP problem? NP problem are those problems for which if you are given the solution, then you can verify the solution is correct or not in polynomial time, right? So for whichever problem that is true, whichever problem you can do that, all will come to NP problem. Suppose NQueen, can you verify the solution? Is the solution correct or not? Yes. So that will come under NP. But easy problems also, let's say your minimum spanning tree. Given a spanning tree, can we verify is it the minimum spanning, is it a spanning tree or not of certain cost? Yes, then it will come under NP. Or even sorting problem. Given a solution, we can verify is it sorted or not in polynomial time. Yes, in linear time we can check it is sorted or not. Then it is also comes under NP. So here NP stands for non-deterministic polynomial. So don't worry about the full form. First try to understand What are the problems that comes under NP? Why it is called non-deterministic polynomial? We can discuss later. The name is given. First try to understand which problems come under it. Okay, fine. So we'll come to this famous diagram which shows 4 classes of problem. So we have class P, that is polynomial, NP, non-deterministic polynomial, NPC means non-deterministic polynomial complete or NP complete, and we have another class NP hard. So whatever computational problem we are solving will fall in these 4 categories. Okay. So first we need to understand which problem falls here. Okay. So as we started with NP. NP means we said that if the solution is given, we can verify in polynomial time. So all such problems will come under NP. Okay. Now we can see P is a subset of NP. So in P, those problems will come for which we have efficient algorithm or polynomial time algorithm. Right. So for example, your shortest path, minimum spanning tree, sorting, these problems we have efficient solution, polynomial time solution, and these problems if your solution is given we can verify in polynomial time also. So this is a P problem is a subclass of NP. Then there are certain problems where there is no known efficient algorithm. Okay. But we can verify it. So these are NP but not P. Okay. And now first let me tell NPC. What is NP complete? So these are the problems. You can see it is an overlap between NP hard and NP. So NPC means a problem will be NP and also the problem will be NP hard, right? Two things has to be there. So NP means already we know NP we can verify in polynomial time, and hard means these are hard problems. Okay, these problems are at least as hard as any other problem here. So there we can say that this problem one of the hardest problem in NP class, right? Now there in between some problems are there which are NP but neither P nor NPC. So these are, we'll see, we will not discuss much about these problems because our discussion mainly will focus on the hard problems, NPC problems. These problems are NP, we can verify it in polynomial time, but not as hard as the problem that lies here. So what are the problems that lies in NPC? For example, your TSP, traveling salesman problem, or Hamiltonian cycle problem. Okay, even your 0-1 knapsack problem. These are lies in NPC. And then there are some problems like graph isomorphism, which are NP, but we don't know any polynomial time solution, but these are not as hard as the problem like TSP or Hamiltonian cycle. And we'll see these problems can be reduced. One problem can be reduced to another. Here we cannot do that. Okay. And the fourth category is NP hard. These problems are only NP hard. So these are not NPC. So given the solution, you cannot verify it in polynomial time, and it is hard problem. So there are problems like Turing's halting problem, where we don't know any efficient algorithm for it, and also if you give the solution, you cannot verify it in polynomial time, right? So these are the four categories. NP means given solution, you can verify in polynomial time. P is a subset of it. Here you can verify in polynomial time, and you also have the efficient algorithm. And then NPC means these are NP and also NP hard, both. Okay, hard problems. And there are only hard problems, right? Fine. So we want to discuss these problems. Basic idea is, if I give you any new problem, how do you prove this belongs to NPC? As we discussed earlier, if you can prove it belongs to NPC, we will not try to solve or find efficient solution, we will manage with heuristic or other way. Okay, fine. So let us discuss that. Okay, so same thing is mentioned here, that class P means problems we can solve efficiently, like sorting, minimum spanning tree. Class NP means here the solution can be verified efficiently, like TSP and Hamiltonian cycle. But all problem in NP does not belongs to P. Okay, all problems in P belongs to NP, but all problems in NP does not belongs to P. So there are some hard problems, and we still don't know the solution for them. But in future, someone may come up with that. So that is an open question. Is NP equals to P? That is, for all problems in NP, is there efficient algorithm? Yes or no? We don't know. It's an open question. Okay. Fine. And then the NP complete class that I mentioned earlier. NP complete means the problem is NP, and also it is as hard as any problem in NP. Okay. And key point here is that if one problem in NP complete can be solved efficiently, all the problems can be solved efficiently. That is a characteristic here. In NPC class, if you can solve problem A efficiently, that will lead to solving problem B also efficiently, or vice versa. So how to prove that, we will discuss that. Fine. These are the example of NP complete problems, and these are all equally hard. And these diagrams I already have drawn. You can see the four classes. You have P, some problems in P given here. Then you have NPC, like Hamiltonian cycle, graph coloring, satisfiability. You have problems which are not P but not NPC also, like factoring, graph isomorphism. And there are problems which are hard and not we cannot verify also, like matrix permanent or Turing halting problem.